Last time I just lost uh, somewhere behind. It didn't work. Things didn't. I mean, I lost my internet. I don't have a very stable network here. Uh, but I don't understand still why it's ah. Maybe I have to. I may. I talked about the creating a cache situation here. I don't know how long I talked about it, by the way. So I'll just start with how do we do the cache. So last time we had this function, the load video function, and this load video function takes a video ID, get all these frames, and combine the video tensor matrix, and we convert them to torch matrix, and all of them would be in uint 8. Um, and that's what we have been doing so far. So when the data loader asks for one index, what it would do is that it would get all the frames, all the frames it needed, and combine it and give it as the inputs, input and target for that respective index to the data loader. And two workers will do separately like this. Two workers will do separately like this. And it is going to take around 20 images for per video, and we have 128 batch size. So eh, for a single batch it will have to do 2560 IO operations, and that's a hell of a task. IO operation is a very worst kind of performance issues that a lot of the problems have. So what I do is that I I kind of save each video's metrics somewhere what we call the cache directory. And when data loader asks for a video, it would check it would check if the cache exists, then give them the cache, or else do 20 IO operations. This will be one IO operation, and this will be 20 IO operations. And the other thing is that we should save the um, tensor in uint8 because it's 4x shorter than the floor 62 432 values, 432. So in that case we only have to store it in small space, as well as when accessing it, it only takes when accessing it, the IO operations don't have to do a lot of sequential scans, sequential IOs, a lot of sequential IOs. Although it's better to do sequential IOs. I don't know how does it actually assign. I guess sequential IO is the right way to go to actually store this kind of information. So if it was random IO, it's going to be a hell of a task for anybody, for the hard disk to do, and it's going to be a lot slower. And if it's 4x larger, it's going to be 4x random IOs, and it's going to be a lot of time. And to avoid all of these cases, we actually store information in uint8, less storage, less data accessing needed, and that's why we're using it. So what we're doing that whenever whenever we initiate the data set, we create a cache before that. if there is a cache directory mentioned, we create the cache directory and perform build cache or perform parallel build cache. I will speak about parallel build before, but these two functions are same, but this do parallelly. This execute this caching thing on multiple threads, but this doing this just in one single thread. So what I would this would take each video ID, and for each video ID, the the cache already exists doesn't exist, it would do the it will extract the 20 frames, create a video tensor, and we save it in a file, something like we save it in this file. We save it in this file. That's what we were doing so far. So this is going to be if this is a single thread, it's going to be taking a lot of time for this build cache to do. So we did do it using parallel build cache using multiple threads, and we created cache for each of these values. And as you can see that if there is a cache, we return the cache. And if there is no cache, we return the actual values. And without cache, it has been taking us like 30 minutes, 38 minutes or something. If we were using uh, CPU, it was taking like 1 hour, 8 minutes, 1 hour, 10 minutes. So there is only 2x improvement on using CUDA out there, more than 2x only. And the main issue actually that happened was this bottleneck issue. So we have avoided those issues using caching. So we would get a better, much faster network right now. I believe so. We don't change method of information here. We also had discussed about how transferring 8 bits from 32 bits. Transferring 8 bits from CPU to GPU is much easier than 32 bits. And so that's why we're doing all these computations before going into this computation after going to GPU. And we use um, this is for logging. Let's see how does it do. Okay, let's see. Let's see how does this caching going to help us, and is it going to give us a very good, is it going to give us very good performance boost or not? And can we actually utilize the entire GPU capability using this? Let's see. Mm, Sub-process. Sorry. A lot of issues, something like a lot of issues related to this is that I can see that using parallel cache input, it does take only 7 or 10 minutes or something. Let's see after that. And until that, you can understand all I already mentioned about uh, using a single model here. And why do we need invalid batches? Actually, that was possibly for. And why do we need this one? This was for other calculations like um for fractional training. We don't want to train our entire data set, maybe just just 0.75 part of the valid batches or train batches. We don't want to train our entire data set. In the cases, we can just limit the data loader for that. And let's see how does it going to perform and mm, without with cache. I wish this was absolutely amazing. And a lot of the cases, a lot of the issues, a lot of the performance issues can be solved. And we have seen right now how do we solve the performance kind of issues related to data transformation. And you can understand how does it, how important would be if we are caching the data set after we finish this caching thing. It's just 7 minutes, and we can see what's the performance gain we have after that. So we actually avoided the bottleneck issues and we reduced the number of IOs. And let's see how it's going to give us, how is it going to improve our training so far. I'm not very good at using all these tools. Not only I'm learning data ML things. I'm just learning all these new things. My videos are being better each day. I think so. Just give your opinions as well. I don't know how does it actually end up. I want to be give you the better. Always, always out there. Okay. Even is this what it's saying or this is what you're saying? I don't know. This is more this thing. Ah, sorry. I'm very new to this. Maybe I can learn this. So, let's do something like that. Studio mode and program OBS in changes in separate window before they appear in your live stream. Sender transition allow for smoothing on the fly. Okay. So we just make things here happen here. Okay, we just make things happen here. Okay, we just change it this one. And we just transition it. Okay, good. That's what that was saying. I'm just learning these things. We're using the same model, and I spoke about it. We just changed the first and the final layer, and the first layer should have 20 channels because we are giving input of 20 grayscale images to the model, and we change our input is just one. We're using transfer learning. I would talk about transfer learning in future, and we are using ImageNet models, ImageNet pre-trained models, and which is RosNet 18. This is a very small model, so we just load the pre-trained weights. We just modify the first and last layer, so we sustain the all the intermediate weights between them, so we don't have to train them or we don't have to tune them a lot, I guess. And we had a train data set, the valid data set, and the batch sizes and number of epochs we have. We use the atom optimizer. I would say, what is atom optimizer and how does it work in future? We're using a binary cross entropy, which logic what logic laws, because the models actually give um linear output. You can say this gives us linear output, and this doesn't should be uh between 0 and 1 for binary cross entropy. Binary cross entropy is based on, like, probability of probabilities, just probabilities, not multi-class. The cross entropy will be on multi-class. Binary cross entropy will be on checking on values of binary cases 0 or 1, and the probability is 0, near to zeros would be good. Probabilities in that manner, loss will be calculated, and those are the informations that it gives, and we compute the loss for mm, each forward step, and in training case we compute the gradient of each weights for the loss. How much does each weight actually contribute to the loss, and we optimize it for every single frames, for every single weights. We reduce, or we just tweak the values according to the gradient value, so that we can reach the um, minimization point as fast as possible. There are reasons why do we don't use learner rate of 1, and we will that's lot of the cases it's not a convex situation. We don't have convex situation, so to avoid that we need some momentum, and we don't want to go greedily approach every single kind of gradient as it is. So it's a very common strategy we use to train. So you can see right now it was 40 minutes. See, it doesn't take a minute at all. Using cache, it doesn't take a minute at all. How fast this is. And the usage of GPUs is absolutely amazing. We can use more batch sizes. That's what we say. That's what it's saying. We can use, like, maybe 2x, or maybe, like, 2.5x batch size right now. It doesn't take a single minute at all. We reduce the um number of operations from we reduce the time from 40 minutes or 38 minutes to just 1 minute. Do you know how great it is, and how fast this training would be? We can finish the training in just 10 minutes. That's what I said. That's the real power of data transformation. That's the real power of caching the data set, caching the data before getting into the neural network. Absolutely amazing, isn't it? See, you can just finish 48 seconds to actually train 11,000 to 300 videos. And you can see the videos are getting decreased every single time. What amazing, right? That's the real power of data transformation. You can just see here. And that's all for this one. I just sorry for making this into two videos. Sorry.